Okay. Have we in fact been live? It hadn't finished going live. No, it had not. Okay, so I'm going to go ahead and start over. I have been talking to myself this entire time. Sweet. Okay, so first problem, chapter 2. Problem 24. Where on the blank outline of the periodic table do elements that meet the following descriptions appear? Elements with the valence shell ground state electron configuration NS2 NP5. Ground state just means stable, lowest energy. No electrons been added, no electrons been taken away, no electrons have been bumped up to a higher thing because of incoming light. Nothing like that. It's just the normal, basic, neutral thing. Now, the N here means that it could be any energy level. So in this case, it could be 2s2, 2p5, or 5s2, 5p5, regardless. It has a full S subshell and an almost full P subshell. So we're looking at the fifth column of the P block. So 1, 2, 3, 4, 5, right here. This entire column meets that, NS2, NP5. It's the halogens. An element whose fourth shell contains 2 p electrons. I choose to interpret that as only 2 p electrons. So 2 p electrons in the fourth shell, so 1, 2, 3, 4 in the p block, and it's only got 2 electrons in the p block, so it's this guy. It is going to be a germanium. Hop over to periodic table, boom, there's germanium. Let's bring up the electrons. And we see germanium, 2 electrons there in the p subshell. Finally, an element with the ground state electron configuration argon, 4s2, 3d10, 4p5. Again, ground state just means neutral, normal. Nothing changed about it. So, AS argon is the one that comes before, and then 4s2, 3d10, 4p5 means that the element we're looking at is bromine. Okay, fifth column of the P block there on the fourth row. All right, now 26. One of the elements shown in the following periodic table has an anomalous ground state electron configuration. Which is it? Red, blue, or green, and why? And it is going to be the green one. Okay, it's near the middle, but not at the middle of the D block. Remember, that's one of the ones you have to memorize, is the anomalous configurations. For this fourth column, can I unselect? I cannot. All right, so this fourth column, chromium, molybdenum, tungsten, seaborgium, and the ninth column, copper, silver, gold, and rentgenium. Röntgen. All right, so these guys all have anomalous electron configurations. The one they pointed out specifically was this one, molybdenum. You would expect it to be 5s2, 4d4, but instead it is 5s1, 4d5. It bumps the electron out of the 5s1 orbital and into this guy right here, what would have been the empty 4d orbital, so that it has a half-full subshell, giving it a lot of resonance. Okay, lots and lots of resonance going on there, making that guy super-duper happy. And 28. What atom has the following orbital filling diagram? Argon 4s2, 3d10, 4p1. Let's assume they mean the ground state. That means 4s2, 3d10, 4p1. It is our friend gallium. Yep, 4s2, 3d10, 4p1. Means it's in the first column on the fourth row of the P block. All right. Who is next? It is, where are we? There we are. 32, 34, 36, 38, 40, 42, 44, 46. Okay, so we're going to go from 32 straight through to 46. Okay. Which has the higher frequency, red light or violet light? Which has the longer wavelength? And which has the greatest energy? All right, this one is pretty much just a matter of memorization for y'all. All right, so if we draw out a very simplified electromagnetic spectrum, we have red light over here at this end, and we have blue light way over here. Well, if we're going with Sir Isaac Newton and his redonkulous, stupid alchemy stuff, then it would be violet, but doesn't really matter. So I have never bothered to memorize frequencies or anything like that, but I do know the wavelengths. Red light. Oops, got that backwards. Red light is at about 700 nanometers. Blue light is at 400 nanometers. So that answers one of the questions. Which one has the longer wavelength or shorter wavelength? Red light has the longer wavelength. Blue light has the shorter wavelength. Okay. Therefore, the frequency is going to operate in the exact opposite direction. Longer wavelength means shorter frequency. Shorter wavelength means higher frequency, I should say. Longer wavelength means lower frequency. Shorter wavelength means higher frequency. So blue light is going to have the higher frequency. Red light is going to have the lower frequency. And energy goes exactly as wavelength. So the way I'm doing these is that the speed of light is equal to wavelength times frequency, lambda times nu. So as one goes up, the other one has to go down because speed of light is a constant. The other equation that I'm using is Einstein's, E equals h nu. That is to say, the energy of the photon is equal to Planck's constant multiplied by the frequency. So as frequency goes up, energy goes up. As frequency goes down, energy goes down. So since blue light has the higher frequency, it is going to have the higher energy. Red light has the lower frequency, therefore it's going to have the lower energy. Okay. Oh dear, I left my soda in the other room. I'll be right back. 5 shakes of a lamb's tail. Remember, a shake is technically like 5 times 10 to the negative 4th seconds. All right. 34. The Hubble Space Telescope detects radiant energy in the wavelength range 1.5 times 10 to the negative 7th meters to 2.0 times 10 to the negative 6th meters. What region of the electromagnetic spectrum is found completely within this range? What regions fall partially in this range? Well, that means that we are looking at 115 nanometers and 20 nanometers. So it is not within the visible range. It is well beyond that. It is in the ultraviolet range is what we're looking at, as far as I can tell. But I don't have ultraviolet memorized in quite the same way that I have the visible spectrum memorized. So let's go ahead and look at the electromagnetic spectrum. Hopefully the chapter has the electromagnetic spectrum well labeled. Ah, look at that. Okay, so it has wavelength up top in meters. So we're looking at, oh no, I had it wrong. Did I? How did I? 10 to the negative 6th means it is higher in energy. So it is not, it is going to be 2000 nanometers. Ah, there we go. There we go. So it is, yeah, well beyond that. So it's going from 10 to the negative 7th down here in the ultraviolet up to somewhere in the infrared. So it will completely cover the visible spectrum. Okay. That's there we go. There we go. So that's how I got that wrong. 2.0 times 10 to the negative 6th. I'm a dummy. I screwed it up. No, I didn't screw it up. One of you guys screwed it up. One of you made that mistake, and I'm going to find out who, and I will punish you. All right. So so this 100 times 10 to the negative 7th is going to be somewhere here in the ultraviolet. Completely covers the visible spectrum and then goes somewhere a little bit into the infrared. I believe the most famous, one of the most famous pictures that we have is from the Hubble Space Telescope. It is called the Pillars of Creation, and I believe that it was taken in the infrared spectrum. Here, let's bring that picture up real quick. As you can kind of see why it's famous. It's just this massive cloud of dust. And it's not the first image of the, it's part of the Eagle Nebula. Most detailed blue colors are oxygen, red is sulfur, green is nitrogen and hydrogen. So it's a false color spectrum. I believe it was taken in infrared. Rather striking. All right, so let's get back to ye old problems. Let's see, I believe we're on page 93. Close. Yeah, no, exactly. Okay, wow. Okay. Next up, what is the wavelength in meters of ultraviolet light with a frequency of 5.5 times 10 to the 15th hertz? Okay, so that is a math problem. We are going to be using this equation right there. C equals lambda nu. So, in fact, let's just go ahead and do it right there. Is equal to lambda times 5.5 times 10 to the 15th per second. So lambda is 2.998 times 10 to the 8th meters per second divided by 5.5 times 10 to the 15th per second. It's going to get us, oh, it's in the infrared. Let's bring up our calculator. So 2.998 divided by 5.5. The answer is 5.4 times 10 to the negative, let's see, 7, then down by 1, so 8 meters, or 54 nanometers. All right. That was an easy one. 38. Calculate the energies of the following waves in kilojoules per mole and tell which member of each pair has the higher value. FM radio at 99.5 megahertz and AM radio at 1150 kilohertz. Okay. Well, just in terms of which one has the higher value, it's going to be the FM radio. Megahertz is a higher frequency than kilohertz. Well, 99.5 megahertz is bigger than 1.15 megahertz. So yeah, the megahertz is higher frequency, therefore higher energy. But calculating the energy, rather straightforward. We're going to be using the Einstein equation, but we're out of room on that particular page. So, where's my purple pen? There it is. All right, so E equals h nu is going to be Planck's constant multiplied by the frequency. So one of them is 99.5 megahertz, so that's 10 to the 6th hertz. The other one is 1150 kilohertz, so that's times 10 to the 3rd hertz. And they wanted it in kilojoules per mole. Okay, so that is going to complicate things only slightly, because this is the energy of an individual photon. So in order to make it per mole, you multiply it by Avogadro's number. So times 6.022 times 10 to the 23rd per mole. So one of them, 6.626 times 6.022 times 99.5. Let's see, negative 34 and positive 23 gives us negative 11. Positive 6 gives us negative 5. Negative 4, negative 3, negative 2. See, that would be joules per mole. They wanted in kilojoules per mole, they did. So that would be 3.97 times 10 to the negative fifth kilojoules per mole for that guy there. The other one, all right, negative 11, negative 8, 7654, so that brings it to 7. 4.59 times 10 to the negative 7th kilojoules per mole. And that is this guy here. Okay. So yeah, it's about 100 times more energy there in the FM band. All right, 2.38b, an X-ray with 3.44 times 10 to the negative 9th meters, and a microwave with 6.71 times 10 to the negative 2nd meters. Well, I can tell you right now, the X-ray is going to have a heck of a lot more energy. It's way higher in the magnetic spectrum in terms of energy. In fact, it's going to be about 10 million times stronger. Just because it has a wavelength 10 million times smaller. All right, so let's do this one in brown. Okay, so once again, we're doing very similar math, but first we have to take into account that they gave us wavelengths instead of frequencies. In that case, it's just E equals hc over lambda, because c equals lambda nu, therefore nu equals c over lambda. If E equals h nu, we just plug in c over lambda for nu, so it gives us the hc over lambda. Okay, so, and then we multiply once again by Avogadro's number to get it into kilojoules per mole. So it is going to be 6.626 times 10 to the negative 34th joule seconds times 2.998 times 10 to the 8th meters per second. I'm writing fairly small because I have a lot of big numbers. 6.022 times 10 to the 23rd per mole, ran out of room, then divided by the wavelength. So one wavelength is 3.44 times 10 to the negative 9th meters. The other wavelength is 6.71 times 10 to the negative 2nd meters. So those are our two wavelengths. They'll give us two fairly different answers. Okay, so here on the left, it's going to be 3.48 times 10 to the what? Oh, wait, no. Okay, so it's going to be kilojoules per mole. Negative 34, negative 11, negative 3, positive 6, then down by 3 makes it 3. Yeah, that was a lot of weird numbers. I'm just trying to get my calculator here on the screen. Doesn't handle scientific notation particularly well, so I'm just letting it do the multiplication of the numbers, and then I'm handling the exponents. All right. So the next one is 6. Now we divide by 6.71. Oh dear. I wasn't paying attention. 1.78 times 10 to the something kilojoules per mole. It's going to be much smaller. But first, let's see the other one. Dang it. Times 6.71 divided by 3.44. There we go. Yeah, I forgot to shift it by 1. Which direction do I shift it? It's getting bigger, so it's going to be times 10 to the 4th. All right, so this one's going to suffer much the same fate. 34, 11, negative 3, -1, +1, then down by 3, so -3rd. Aha! Wow, my numbers work out exactly right. It's off by 10 million. A factor of 10 to the 7th. Our wavelengths were different by a factor of about 10 to the 7th. Therefore, our energies are different by a factor of 10 to the 7th. So no surprises there. All right. Number 40. A certain cellular telephone transmits at a frequency of 825 megahertz and receives at a frequency of 875 megahertz. What is the wavelength of the transmitted signal in centimeters? And what is the wavelength of the received signal in centimeters? All right. Rather straightforward. Whatchamacallit? Translation. C equals lambda nu problem. Okay, so you'll focus soon enough. C equals lambda nu, or lambda equals C over nu equals 2.998 times 10 to the 8th meters per second divided by the two different frequencies. So for the first one, we have 825 times 10 to the 6th hertz. The other one is 875 times 10 to the 6th hertz. This will give us our wavelength in meters. Down by 2. Oh. It is, that worked out quite nicely. Neato burrito. No, it should be -1, shouldn't it? Yes, it should. And the other one will be very similar. Because the other one is going to be 3.42. Oops. 3.42 times 10 to the -1st meters. So that is to say 0.363 meters, 0.342 meters. So to translate those to centimeters, you multiply them by 100. So 36.3 centimeters, 34.2 centimeters. Thus putting them neatly within the radio wave. All right. What is the wavelength in meters? Oh, you can't see the problem. What is the wavelength in meters of photons with the following energies? In what region of the electromagnetic spectrum does each appear? Okay, no questions. All right. Okay. So in this case, we're translating from energy to wavelength. So once again, we are using this guy here, E equals hc over lambda. So lambda equals hc over energy. But in this case, they give it the energy to us in kilojoules per mole, so we have to include Avogadro's number in there. I don't know why they do that. Well, there might be a very good reason. Well, there is a very good reason. It gives us a number that is somewhat more reasonable. Instead of being times 10 to the -19 joules per photon, it's, kilojoules per mole in realistic sorts of numbers, I suppose. So it's not the worst thing in the world. Oh, but that gives us to us in joules per mole. So I'll just go ahead and translate to joules when I put the numbers in. All right. So our first one is 90.5 kilojoules per mole. So it's going to be 6.626 times 10 to the -34th joule seconds times 2.998 times 10 to the 8th meters per second times 6.022 times 10 to the 23rd per mole And this first energy is 90.5 times 10 to the third joules per mole. They gave it to us as 90.5 kilojoules per mole, so I just translated it to joules. That way the joules here will cancel out. The seconds will cancel out there. I'll go ahead and mark those off. Joules cancel, these per moles cancel, and seconds cancel, leaving us with meters. Oh, you can't see. All right, now you can see. Okay. So we plug the numbers into the calculator. 6.66 times 6.022 times 2.998. Now we divide by our energy, 90500. Giving us a length. Oh, that looks to be in the radio wave region of the spectrum. 0.00132 meters. That's 1, 2, 3, 4, 5, 6. 1320 microns. Yeah, that's out in radar, I think. Let's see, the next one, same sort of math, only instead of 90.5 kilojoules per mole, it is 1.83 times 10 to the third kilojoules per mole. So I'm going to go ahead and translate that directly into joules per mole. So get rid of the kilo, turn this into a 6. And what sort of wavelength is that? So we're now dividing by 183, 1, 2, 3, 4. That is, oh dear, that is not right. I mean, I got the number right, but 0.00132, negative 34, negative 11, negative 3, positive. Oh, it was exactly right. It just worked out that way. So this was correct, 0.0132 meters. Okay. All right, but in this case, it's going to work out slightly differently because we have a different exponent here. So negative 34, negative 11, negative 3, positive 3. So we're going to, so it's going to be 6.54 times 10 to the negative 2, or 0.0654. Well, that can't be right. It's nearly 1,000 times bigger. It can't be. Oh. Oh dear. Okay, so I see what I did. Okay. So let's try this again. So times. All right. So now divide by 90.5. Okay. So that means that this is 1.32 meters, just because of the way the math works out. Okay. Now, 1.32 meters is definitely way out in radio waves. So now divide by 1.83, and that's going to end up being positive 3. Okay. See, this is why you got to be really careful when you're trying to do math and stuff while tired. Okay, so that is going to be 65.3 times 10, 0.4 times 10 to the third meters? Really? That is way the hell out there. I went in the wrong direction. That's what I did. Okay, so negative 34, negative 11, negative 3, then down by 6, it should be negative 9, not positive 3. There we go. 65.4 times 10 to the negative 9th meters, or 65.4 nanometers, which puts it solidly in ultraviolet. Hoop-a-doof. Okay, and the last one, 8.05 times 10 to the negative 4th kilojoules, or 8.05 times 10 to the negative 1st joules per mole. Plug it in for the same sort of math. negative 34, negative 11, negative 3, negative 2. So it is 14.8, 14.9 times 10 to the negative 2 meters, or 0.149 meters, or 14.9 centimeters, which puts it more in the realm of radar, I think, than it does radio. But let's go ahead and go back to page, I think it was 62, that had the, yes it does. So wavelength in the meters is going to be radio. Wavelength in nanometers, let's see, nanometers, yep, just beyond here would put it into the ultraviolet. And 14.9 centimeters, we're at the boundary with microwaves. Okay, all right. No questions. All right, what problem are we on now? That was 42. I believe we go up to 46. Yes, we do. 44, then 46. The data encoded on CDs, DVDs, and Blu-ray discs is read by lasers. What is the wavelength in nanometers and the energy in joules of the following lasers? Oh, it didn't ask for joules per mole. Good. Good, 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 good. All right, so for wavelength, let's see. Wavelength is C over nu. Energy is H nu. Okay, so it's just really simple, straightforward math for each of these. So for the first one, we're looking at a wavelength of, a frequency of 3.85 times 10 to the 14th. So 2.998 times 10 to the 8th divided by, I've already forgotten it, 3.85 times 10 to the 14th. So that is 0.778 times 10 to the negative 6th, or 7.78 times 10 to the negative 7th meters, or 778 nanometers, making it, that might be red if you have a particularly good set of eyes, but that's near infrared. The energy is 6.626 times 3.85. So that is going to be 2.55 times 10 to the negative 19th joules for that particular photon. That was A. Next up, DVD is 4.62, and then Blu-ray is 7.41. Higher frequencies, so they're getting higher energy, which means it's going to shift from infrared into the visible spectrum as we go along. So 2.998 divided by 4.62. Yep, that's 648 nanometers, or 649 nanometers, making it red. And then 6.66 times 4.62. And that is 3.06 times 10 to the negative 19th joules. And then the next one is probably going to be in the orange, possibly yellow, 7.41. Oh, it's actually almost double. Well, we'll see. It might even be as far as green. All right, 7.41. So 2.998 divided by 7.41. That's going to be 404. That is solidly blue. 404 nanometers. And then 6.66 times 7.4. Oops, I don't even have my calculator up. 6.66 times 7.41 is 4.91 times 10 to the negative 19th joules. All right. 2.46. According to the equation for the Balmer line, the spectrum of hydrogen, a value of n equals 3 gives a red spectral line at 656.3 nanometers. A value of n equals 4 gives green at 486.1, and a value of n equals 5 gives blue at 434. Calculate the energy in kilojoules per mole of the radiation corresponding to each of these spectral lines. Okay, well, once again, E equals hc over lambda. But we have to throw this in there because they're asking for it in kilojoules per mole. So 6.626 times 10 to the negative 34th joules seconds times 2.998 times 10 to the 8th meters per second times 6.022 times 10 to the 23rd per mole divided by our wavelengths, which are 656.3 times 10 to the negative 9th meters, 486.1 times 10 to the negative 9th meters, and 434.0 times 10 to the negative 9th meters. Okay, so three separate numbers will give us three separate answers. This here is red. This one is our green. And this one is our blue. Calculator needs to be up before you can type. So, 0.182, 34, negative 11, negative 3, positive 6. So, 1.82 times 10 to the 5th. Oh, they want it in kilojoules per mole, so bring it down, 10 to the 2nd kilojoules per mole, or 182 kilojoules per mole. So they're all going to be at about that range. So, boop, divided by 486.1 for 246 kilojoules per mole. And then 434 for 893 kilojoules per mole. And with that, we are done with a long-ass, boring section of algebra, doing the same problem over and over. Let's do 258. What are the four quantum numbers, and what does each specify? All right, well, they have the technical specifications, and then they have what we call them. Okay, so the four quantum numbers are N, L, M sub L, M sub S. So technically, this is the principal quantum number, this is the azimuthal quantum number, this is the magnetic quantum number, and this is the spin quantum number. Those are the ones I've never asked anyone to memorize ever. Instead, I just say level, sublevel, orbital, and still spin. Because that is a hell of a lot easier to remember than principal, azimuthal, magnetic, and spin. Level, sublevel, orbital, spin. So these three define where in space you can find the electron around the nucleus, and this tells you about the orientation of the electron, spin up or spin down. So what floor, what suite, what room, top bunk or bottom bunk. 62, 64, 66, 68. So all the 60s, except for 60 itself. What is meant by the term effective nuclear charge, and what is it due to? All right, effective nuclear charge. We're talking about the electrons and the nucleus. So at the center of the atom, you have the nucleus, chock-a-block, full of protons. Around that, you have this big old set of core electrons. And then all the way on the outside of the atom, you have the interesting guys, the valence electrons. So, electrons are negative, hence I put the negative sign there. Protons are positive, hence the positive sign. And thus, the electrons are attracted to the protons. The electrons are drawn in by the nucleus. That's why they stay around the atom. But in between the valence electrons and the nucleus, you have this big, stupid shield of core electrons. So the effective nuclear charge, ZF, is equal to the number of protons minus the number of core electrons. But fortunately, you don't have to do that math every time because it ends up being equal to the number of valence electrons. So the effective nuclear charge corresponds to the amount of the nucleus's pull that makes it through the shielding of the core electrons in order to pull on those valence electrons. How much of the nuclear charge reaches through the shield to get to the valence? 64. Give the allowable combinations of quantum numbers for each of the following electrons. A 4s, a 3p, a 5f, a 5d. All right. What the heck? That was weird. Okay, I just did a thing. Okay, this is easy enough to fix. All right, and it's fixed. Okay. I accidentally dragged a thing, and it totally changed the arrangement of stuff. But, all right, so the allowable quantum numbers. All right, so first up, we have 4s. So let's do purple. I haven't done purple in a while. 4s. So 4s nails down a lot because that right there is n equals 4, and that is L equals 0. So that locks down two of our quantum numbers. All that's left is m sub L, which can, for this guy, only be equal to 0. M sub L is based on L. It goes from negative L to positive L. So it can only be 0. And then m sub S is, of course, plus or minus 1/2. So 4s can only hold 2 electrons because there's only the one orbital in the 4s subshell, and that one orbital can only hold 2 electrons, one spin up, one spin down. Next is 3p. So for n equals 3 and L equals 1. So for L equals 1, m sub L can be anywhere from negative 1 to positive 1. Okay, negative 1, 0, or positive 1. And m sub S, likewise, can still only be plus or minus 1/2. So the 3p subshell can hold 6 electrons. 2 electrons, one spin up, one spin down, in each of its 3 orbitals. Okay, so for a total of 6. 5f. N equals 5, L equals 3. So m sub L is equal to, well, positive 3, positive 2, positive 1, 0, negative 1, negative 2, or negative 3. And once again, m sub S can only be plus or minus 1/2. So an F sublevel or subshell can hold 14 electrons. 2 in each of those orbitals, and there are 7 total orbitals. Finally, 5d, n equals 5, L equals 2. So m sub L can be -2, -1, 0, +1, or +2. And m sub S is still just plus or minus 1/2. All right, and that is 64. They will definitely, absolutely ask you something about this, just to make sure that you actually do have the numbers in your head in some way, shape, or form. So next problem is 66. This is another thing that they're almost certainly going to do, is asking you which of the sets of numbers is not possible. Which of the following combinations of quantum numbers are not allowed? Explain your answers. A, B, and C. All right, so I'm going to go ahead and recopy this onto the page so I can go through each of them. All right. So we have A, B, and C. We have N, L, M sub L, M sub S. And for A, we have, oh no, we don't have M sub S. We just have N, L, and M sub L. Okay. So 3, 0, 0. Oh, wait, no. 3, 0, and -1. For B, we have 3, 1, and 1. And for C, we have 4, 4, and 0. All right. So which is allowed, which is not allowed? So n can have any value for any positive integer. So 1, 2, 3, 4, etc. So all three of these are perfectly fine when it comes to n. Not a problem there. L is any non-negative integer less than n. So it can be 0, 1, 2, 3, any number, not negative, but less than n. So 0 is less than 3, not a problem. 1 is less than 3, not a problem. 4 is not less than 4. So that means that C is out because L has to be less than 4. All right. Now M sub L can be any value from -L to +L, which means that if L is equal to 0, M sub L can only be equal to 0. So this one is out. The M sub L has to be less than or equal to the absolute value of L. That's one way of putting it. Or -L is less than or equal to M sub L is less than or equal to L. All right. So for M sub L equals 1, that's not a problem. L is equal to 1, so M sub L can be equal to 1. And then we don't even bother with this one because we already ruled it out based on L. Okay, so A doesn't work, C doesn't work, B does work. All right. Oh, and 68. What is the maximum number of electrons in an atom whose highest energy electrons have the principal quantum number n equals 5? Okay, so for n equals 5, technically you can have L equals 0, 1, 2, 3, and 4. Really, we would not ever actually go to sublevel 4 because this is S, P, D, F, and G. Real atoms don't really go out there, but we could. So I don't know if the problem is going to count that or not. So number of orbitals. Okay, so M sub L goes from -L to +L, so it's going to go up by odd numbers. So the number of orbitals is 1, 3, 5, 7, and technically 9. So you can have 2 electrons in each orbital. So that means you can have 2 electrons there, 6 electrons, 10, 14, and technically 18. So depending on whether or not they're expecting you to count the G sublevel, you could have 2, 8, 18, 32 electrons, or 50 electrons in the 5th energy level. I'm not sure which they would expect from you, and thus I don't think that Bruce would throw that at you on the test. Oops, that's what I wanted to look at, and yeah, okay. So actually I'm going to pop to the back of the book and see what they expect from this problem. All right, so appendix, answers to selected problems. We're going to chapter 2, question 68. It will occur when the 5G orbital is filled, and thus you would expect, the total number of electrons, not just the number of electrons in that. That's sneaky. So let's see. For n equals 4, the total number was 36. No, because it doesn't include these, so that means that it goes up to 50. Then the additional 50? Oh, 60, because, God, what an annoying problem. But really, 138 electrons? That is a very poorly, because they're, I don't like that problem. All right, so we're on page 94. Oh, the highest. Okay, so it's not just. Okay. I see what they were going for there. I still don't like it. That's weird, really, really poorly worded problem. All right, 72, 74, 76, 78, 80, 82. So 72 to 82. Sodium atoms emit light with a wavelength of 330 nanometers when an electron moves from 4p to 3s. What is the energy difference between the orbitals in kilojoules per mole? All right, they're making this look more difficult and complicated than it actually is. They're just asking you to find the energy related to that wavelength, which means that you're still just doing E equals hc over lambda. Come on, focus, buddy. You can do it. There you go. That's right. Yeah. Except it was in kilojoules per mole, wasn't it? Yes, it was. So we tack Avogadro's number on there. So, 6.626 times 10 to the negative 34th joule seconds. 2.998 times 10 to the 8th meters per second. Times 6.022 times 10 to the 23rd per mole, divided by 330 times 10 to the negative 9th meters. All right, when you see nanometers, you can just go ahead and just change it to meters by tacking times 10 to the negative 9th on there. Don't move the decimal place if you do it like that, though. All right. So we plug those into Mr. Calculator. Oops. All right, 34, negative 11, negative 3, positive 6. So 3.63 times, technically it's just 3.6. Times 10 to the 3rd kilojoules per mole. My finger is all covered in marker. All right. 74. Why does the number of elements in successive periods of the periodic table increase by the progression 2, 8, 18, 32? That's nice. That's because we are looking at increasing numbers of sublevels with increasing numbers of electrons, or with increasing numbers of orbitals. S only has 2. P gives us 6 more for 8. D gives us 10 more for 18. And F gives us 14 more for a total of 32. 76. In a multi-electron atom, which orbital in each of the following pairs is higher in energy? 5p or 5d? 5d. Just D is going to be higher in energy than P. 4s or 3p? 4s. 4s is filled after 3p. 6s or 4d? That is going to be 6s. Okay. Because here is the 4d in this row, and then 6s is boom, boom, one lower than that, meaning that it is higher in energy. Okay. Oh, you couldn't see, but 4d is up here, yttrium to cadmium. 6s is down here, cesium and barium. So cesium and barium are higher in energy than yttrium to cadmium. All right. 76. We already did that one. 78. According to the Aufbau principle, which orbital is filled immediately after each of the following in a multi-electron atom? 4s is going to be followed by 3d. 3d is going to be followed by 4p. 5f is going to be followed by 6d. And 5p is going to be followed by 6s. Okay. Those are all right there on the periodic table. 4s is followed by 3d. 3d is followed by 4p. 5f is this guy down here, and that's going to be followed immediately by this one, 6d. They're both in the 7th row, but remember f is shifted by 2, d is shifted by 1. And then 5p, this guy here, is going to be followed immediately by 6s. 80. Give the following ground state electron configurations for the following elements. I'm going to do the abbreviated electron configuration because I want to save myself some time in space. All right, so titanium, ruthenium, tin, strontium, and selenium. Titanium, ruthenium, tin, strontium, selenium. You can't see what I'm writing. All right, first up is titanium. Titanium is element 22. The previous noble gas is argon, and then it's in the second column of the 3D. So we're going to stop at 3D. Okay. So, boom. Argon, 4s2, 3d2. No trouble there. And then we can come back and we can check my answer on the periodic table by clicking here. Argon, 4s2, 3d2. Next up is ruthenium, element 44. So it's in the 6th row, or sorry, the 6th column of 4d. So 1, 2, 3, 4, 5, 6 gets us to ruthenium. Previous noble gas is krypton. So it's going to be krypton, 5s2, 4d6. Once again, we check our answers really easily. Just click on ruthenium, let the web page do its thing. 5s1, 4d7? That's nonsense. That's foolishness. I can understand it, but I don't like it. I do not like it, sir. No, sir. That is not at all like iron. Iron is well behaved, 4s2, 3d6. Osmium probably does the same thing as ruthenium. It does not. Osmium is also well behaved. What the hell is going on with ruthenium? Okay, so things being what they are, you do not have to remember this exception. Because it's probably not an exception in their textbook. So I'm going to stick with my answer. My answer is technically correct. The best kind of correct. All right, so next up is 10, element 50. Previous noble gas is krypton. So krypton, 5s2, 4d10, 5p2. I expect 10 to be very well behaved. And yep, there it is. 5s2, 4d10, 5p2. Next up, strontium. Strontium is over here in the S block. Previous noble gas is also krypton. So I'm not even going to bother to check on this because it is not even possible for it to have an anomalous configuration. Now, selenium is over here in the P block. Element 34. Previous noble gas is argon. It's in the fourth row. It's in the fourth column of the P block. So it's 4s2, 3d10, 4p4. Being able to fill those in is useful. Don't forget that there are exceptions that they will expect you to know. They will expect you to know the chromium column and the copper column. Remember those. Remember those are exceptions because they bump an electron up from the S into the D in order to give a half full for the chromium group or completely full for the copper group, D subshell. Okay, that was 80, now 82. I believe that's what's next. Yes, 82. Draw orbital filling diagrams for the following atoms. Show each electron as an up or down arrow and use the abbreviation of the preceding noble gas. Okay, thank goodness. So they don't expect us to do every single electron. This is an abbreviated orbital filling diagram, as it were. So, rubidium, tungsten, germanium, and zirconium. All right. So, rubidium. Rubidium is right... Oh, you can't see it. It is right here. And the previous noble gas is krypton. So, krypton, it has one electron there in its 5s subshell. Nice and easy. Tungsten, only slightly more difficult. You can just barely not see it. It is right here, element 74. Previous noble gas is xenon. Okay, so to make this easy, we're going to go from 6s up to 5d. And don't forget the F block there in the middle. So, 6s, one up, one down. 1, 2, 3, 4, 5, 6, and 7. That's 4f. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then tungsten is in the fourth column of the 5d. 1, 2, 3, 4, 5. 1, 2, 3, 4. Which means that it is an exception. We are going to bump this guy out of 6s up into 5d. Okay, so it is 6s1, 4f14, 5d5. All right, germanium. You can see him. He's on the fourth row. He's in the second column of the P block. Previous noble gas is argon. So, argon, 4s, 1, 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4p, 1, 2. And finally, we have zirconium. Zirconium, you cannot see him right now, but we'll bring him up. He is right here. He is in 4d. He's in the second column. So the previous noble gas is over here is krypton. So, four D means we start at 5s before going on to 1, 2, 3, 4, 5, the 4D. So 1, 2, 3, and 4. Because he's in the second column of the D block, he only has 2 electrons there in 4D. Okay, next up is 86. How many unpaired electrons are present in each of the following ground state atoms? All right, this is one of those occasions where you have to be able, oops, dang it, where you have to be able to do orbital filling diagrams, because orbital filling diagrams show you whether electrons are paired or unpaired in a way that electron configurations don't. Okay. So we're going to have to do orbital filling diagrams for oxygen, silicon, potassium, and arsenic. Okay, so oxygen, silicon, potassium, arsenic. Okay, oxygen, previous noble gas is helium. Okay. And you can see him over here in the P block, second row, fourth column. So, one, two, three, and four. So oxygen has 2 unpaired electrons. That's the answer they're looking for. How many unpaired electrons? Silicon is in the second column of the third row. So the previous noble gas is argon. 3s, 3p, 1, 2, 3, and 4. Silicon likewise has 2 unpaired electrons. It gets there via a different path. It has a different total number of electrons. So it's going to behave differently from oxygen, even though they have the same number of unpaired electrons. Potassium is the first column of 4s. Previous noble gas is argon. I screwed up a silicon. Previous noble gas from krypton is argon, so 4s, a single unpaired electron. Finally, arsenic. Arsenic is underneath phosphorus there. Previous noble gas is also argon. 4s, 3d, 4p, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then it's in the third column, so it has 1, 2, 3 unpaired electrons. All right. And here comes the cat. All right, so what problem comes next? After 86 was 88. 90, 92, 94, 96. Okay, so we're going all the way up to 96. At what atomic number is the filling of a g orbital likely to begin? Oof. Oofa doofa. Ugly, ugly question. Okay, so if we were to achieve d orbital status, we're looking at 1s, 2s, 2p, 3s, 3p, 4, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, 6s, 6p, 6s, 6f, 7s, 7p, 7, oops, d, 8s, 8, 8p, 8, oops, then we need to go there, and finally 9s. The reason I'm doing it like this, as you'll see, when we do Aufbau using this method, we do it in a sort of downward arrow style, telling us which sublevel gets filled next. Okay, so 5G will come right after 8S. So 8S, pop it over the periodic table, doesn't technically really exist yet. We take this away, but that would be atomic numbers 119 and then 120. and then we would start filling 5G. Oh no, it's not even 8s, it's 9s. God. So 8s would be followed by 6F, so 1920 plus 14 from the Fs makes us 34. 10 more from the D gets us 44, 144. Then 6 more brings us up to 150. Then 151, 152. Then 8G begins filling. No, sorry, 5G. Oh, no, I had it right the first time. 8S, then 5G. So 119, 120 begins filling at element 121. What a pain in the keister. Because 5G, then 6F, then 7D, then 8P, then 9S. So 8S is followed by 5G. I had it right the first time. So 119, 120, then element 121 would be where we would begin filling 5G. But you can see that's why we don't bother with G sublevels. You have to go way down here into fictional, well, not fictional, just elements that haven't been created yet. Everything up to, I believe it's uranium, exists in nature. Uranium is the heaviest element you can find in nature. Everything after that had to be man-made. So from neptunium all the way through to oganesson. There we go. Oganesson, I don't know. Those are all artificial elements. So are some of the lighter elements like promethium. Let's see, technetium is an artificial element. I think that's it. Oh no, francium and radium. Those are both. Well, francium isn't. It's kind of artificial. Radium is also artificial too. Radon is not artificial. Astatine, I don't know. Polonium, I'm not sure. But radon, I know, can be produced naturally. It is a problem in some homes here in the upstate. I know that. My grandfather had a radon detector. I haven't been in a house with a basement in the upstate in quite some time. Not since my grandparents died, in fact. So I don't know if that's still a problem. It probably is, but it's produced. It's a product of natural radioactive decay that you get in some minerals here in the upstate, and thus it will seep into basements. All right, next problem. That was 88. So next up is 90. Why do atomic radii increase going down a group? That's because every step you take going down is a step out in energy. A step down is technically a step up in energy. So you're going out in energy level. That's why they get bigger. Energy levels, a higher energy level is literally further away from the nucleus. 92. Order the following atoms according to increasing atomic radius: sulfur, fluorine, and oxygen. So we look at the periodic table of sulfur, fluorine, and oxygen. Okay, nice and straightforward. Oxygen and fluorine are in the same row. Oxygen and sulfur are in the same group. Fluorine is going to be the smallest. Up and right is smallest. Every step you take left, you get bigger, so oxygen is bigger than fluorine. Every step you take down, you get bigger, so sulfur is bigger than oxygen. So fluorine is the smallest, sulfur is the biggest, oxygen is right there in the middle. 94. The amount of energy that must be added to remove an electron from a neutral atom to give a positive ion is called the atom's ionization energy. Which would you expect to have the larger ionization energy, sodium or magnesium? All right, so larger energy means you have to work harder to remove that electron. If you're working harder, that means that the nucleus is pulling harder on those electrons, which means that you would expect magnesium to have the higher ionization energy because it has a higher effective nuclear charge. Its protons are better able to reach through the shield and grab a hold of its valence electrons. So you would expect it to have a higher ionization energy. And I believe 96 is next. Yes, 96 is the last one in this group. What is the expected ground state electron configuration of the recently discovered element with Z equals 116? Go to our periodic table. 116 is Livermorium, named after someone named Livermore, apparently. So it is in the P group. It is in the fourth column of the P block. It is in the seventh row. So, Livermorium. quoth the raven, Livermore. So that is LV. Previous noble gas is radon. So we're looking at 7s2, 5f14, 6d10, 7p4. Ground state electron configuration for livermorium. All right. And the final problem of this chapter, problem 104. There we go. What is the energy? Go to hell. They mix it up a little bit by giving two of them to us in frequency and one of them in wavelength, but god damn it. You know how to solve these by now. I'm not even going to bother. I'm tired. It's late. I'm going to call it